Correlation does not imply causation, is a phrase used in science and statistics to emphasize that a correlation between two variables does not necessarily imply that one causes the other. For example, every person who learned math in the 17th century is dead. However, learning math does not necessarily cause death. Correlations can help us search for cause and effect relationships, but causality is not the only possible explanation for a correlation. For example, children with bigger feet tend to read better than children with smaller feet. But bigger feet will not cause a child to be a better reader. In this case, there is an underlying cause. Children with bigger feet also tend to be older and have been in school longer. For another example, the more firemen fighting a fire, the bigger the fire is observed to be. However, more firemen does not cause the fire to increase. So, possible explanations for correlation. Number 1, the correlation may be a coincidence. Number 2, both variables might be directly influenced by some common underlying cause. Number 3, one of the correlated variables may actually be a cause of the other. Note that even in this case, we may have identified only one of several causes. A coincidence is a sequence of events that, although accidental, seem to have been planned, arranged, or correlated. Some examples include, as stock prices go up, skirt lengths get shorter. As Internet Explorer's market share decreased, so has the U.S. murder rate. As the number of pirates in the world decreased, global temperatures have increased. An underlying cause, sometimes referred to as a lurking variable or confounding factor, is an overlooked variable that is actually causing a sequence of events to seem to be correlated. Some examples include ice cream sales reflect the number of shark attacks on swimmers, but really the season of the year is the cause. Sleeping with one's shoes on is strongly correlated with waking up with a headache. Well, usually alcohol is the cause of that. We say one event causes a second event when the second event is a consequence of the first. Some examples include flossing regularly reduces gingivitis. Every time the sun goes down, it gets dark outside. Flattering your statistics instructor will give you better grades. That's just a joke. That's not real. Here's example 5. Describe a possible explanation for each correlation. A. When I exercise regularly, I tend to lose weight. Okay, a possible explanation could be that this is a cause. This is causation. That exercise really is causing me to lose weight. But an underlying cause might be diet or supplements, or both. Part B, cities with more homicides also tend to have more churches. Now, I don't think this one is a cause, okay? However, an underlying cause could be the size of the city. Okay. I guess it could be causation, because if a city had a lot of murders, then people might think there was a need for a lot of churches and they might build more churches, so maybe it's causation. And then maybe it's just a coincidence. Part C, with a decrease in the wearing of hats, there has been an increase in global warming over the same period. Well, I don't think not wearing hats is causing the global temperatures to rise, so this is probably just a coincidence. And yeah, there are probably a lot of underlying causes of global warming. If we are convinced that the association we are examining is linear, then the regression line provides the best numerical summary of the relationship. But how good is quote-unquote best? A common way to explain the strength of a linear fit is the coefficient of determination, r squared. Literally, it is the correlation squared, and describes the amount of variation in the response that is explained by the least squares line. So here's example 6. Find the regression line for the data below. What are r and r squared? So in the TI-84 calculator, we would put the x values in list 1, the y values in list 2. Then we would use that same process with stat, and then tests, and then linear regression t-test. Okay, and all that good stuff, and get our answers. So the prediction line for the regression line would be of the form y hat equals a plus bx. So in our results from our calculator, the a is 3.47 and the b is 0.526x. The little r is 0.7947 and r squared is 0.6316, which is approximately the r number, but just squared. Okay. Because r is always between -1 and 1, r squared is always between 0 and 1. Often, r squared is written as a percent. A value of 100% means the relationship is perfectly linear and the regression line perfectly predicts the observations. A value of 0% means there is no linear relationship and the regression line does a very poor job. In the previous example, the correlation between x and y was r equals 0.7947. So the coefficient of determination is 0.7947 squared, which equals 0.6316, which we report as 63.2% rounded. So moving the decimal 2 places to the right makes it into a percentage. What does the value of 63.2% mean? A useful interpretation of r squared is that it measures how much of the variation in the response variable is explained by the explanatory variable. For example, 63.2% of the variation in the y values can be explained by the x values. The 84 students that took the final exam are shown below. X is the exam 1 score, and Y is the final overall grade. We can see that R squared is 43.47%. So this means that 43.47% of the final grade is explained by exam 1. When X averages exams 1 and 2, the coefficient of determination goes up to 67%. So in other words, we have more information in the X values now. So here's our R squared. So this means that 66.79% of the final grade is explained by both exams 1 and 2. When X is the average of all 3 exams, the coefficient of determination goes up to 80%. So we have even more information in the X values. When X includes the final exam, the coefficient of determination goes up to 92%. Even more information in the X values. Adding homework to the exams explains away almost all the variation. So we have even more information in the X values now, and the R squared is 96.75%. After final exam scores have replaced the worst midterm, if it helped, the correlation is perfect. So now we have R squared equals 100%. Here's example 7. If a linear model has a correlation of negative 0.87, so this is the correlation coefficient, how much of the variation in the response is explained by the explanatory variable? So we would calculate R squared, which is negative 0.87 squared, which equals 0.7569, which is the same thing as about 75.7%. Part B, if a linear model has a strong negative relationship with a coefficient of determination, that's R squared, of 0.48, then what is the correlation coefficient? So if R squared is 0.48, then R is the negative square root of that because it said it was negative. So that's about negative 0.6928.